Hi, and welcome to our presentation titled Leveraging Cloud to Accelerate Library Characterization by Mentor at Siemens Business. Today, we're going to talk about how engineering teams can utilize the scalability and performance of cloud platforms to speed up the runtime intensive task of characterizing timing libraries. My name is Wei Tan, and I'm the product manager for library characterization tools here at Mentor. Before this, I'd worked in various roles in digital and analog design and EDA, so I've always had a pretty big interest in library characterization. Here's the agenda for today. We'll start with a brief overview of timing library characterization and what the current challenges are. Then we'll talk about how cloud computing resources can be used to address some of the challenges that we normally encounter. We'll also take a look at an example cloud deployment configuration and discuss some of the best practices for deploying your workflow on the cloud. After that, we have a case study where we tested the scalability running on Microsoft Azure's cloud platform, followed by a wrap-up and summary. In the past couple of years, we've seen an increase in interest from our customers to start using cloud resources to address peak compute capacity needs or even move most of the compute work done to the cloud. Although there are many EDA tasks that can and are deployed on the cloud, our talk today focuses on library characterization done on the cloud. We'll show in the next few slides, since library characterization is comprised of millions of loosely coupled jobs, it readily takes advantage of the scalability of resources available on the cloud. There are significant advantages both in scalability and meeting peak capacity demands by deploying on the cloud. However, when we're running EDA tasks on the cloud, we need to consider security in addition to performance and cost effectiveness. All these go hand in hand. Finally, I also wanted to mention here that in addition to a library characterization platform, other Mentor AMS verification tools are cloud ready and tested, including Solido Variation Designer, as well as Mentor Spice simulators like AFS and Aldo. With that, let's dive into our discussion on cloud characterization. For modern digital chips that consist of many millions of transistors, timing validation is achieved by running static timing analysis, or STA for short. Due to the complexity and skill of full chip or even block level timing, very little SPICE simulation is done at that level. Instead, STA uses timing libraries, or DOLIPs for short, as the basis for calculating timing properties of all logic paths in the design. Library characterization is the process of producing highly accurate timing models for digital design and sign-off. As shown here, at the chip or block level, digital designs comprise of lower level building blocks such as standard cells, IOs, memories, and analog blocks. By pre-running SPICE simulation on these library components, library characterization extracts timing properties into the lib files so that the STA tools can then use a lookup table-based method to calculate timing at the block or chip level. As with most other EDA tasks, there are many challenges to library characterization that our tools address. For the purposes of staying on topic though, I'll just focus on the scheduling and resource challenges here. The main challenge we're facing in this aspect is runtime. Library characterization requires many SPICE simulations to fully characterize a library. Let's take standard cells as an example. The modern standard cell library has on the order of 1,000 cells. Doing the math on how many SPICE simulations are needed for a typical 7 nanometer library, we find that we will need a few hundred million SPICE simulations to characterize each revision of that library. And that's just for base characterization, not including the statistical variation modeling, which will further the number pretty significantly. This is why library characterization jobs are usually assigned hundreds to thousands of compute nodes and still take days or even a couple of weeks to complete. Most larger semiconductor companies have on-premises server farms ranging from hundreds to thousands of CPUs. These CPUs are used for a variety of tasks, but due to the number of libraries required to support all design teams, peak demand for CPUs for library characterization can still slow down production schedules. For smaller companies, having a compute farm of thousands of CPUs may not be feasible because there may not be as many design teams needing different libraries. So investing in a huge server cluster may lead to underutilization during downtimes. All these hardware limitations of on-premises systems can be addressed using cloud platforms. Let's take a closer look to see how cloud computing can help address these challenges. We know library characterization takes transistor models and SPICE circuit information as inputs. Transistor models come from the foundry PDK, while the SPICE circuits of the library components come from the library design team. This will, for example, be SPICE circuit netlists of standard cells. The library characterization tool then runs a large number of SPICE simulations and writes out timing.lib files used by synthesis, by placement route, and sign-off STA tools. Under the hood, what's really happening is this. A main dispatcher process launches the many SPICE simulation jobs across the assigned CPU pool, either directly or via an LSF or grid engine load balancing system. Each individual SPICE simulation job doesn't really take too long to complete. The runtime may vary, but it's usually measured in minutes, barring any exceptional cases. These SPICE simulation jobs are mostly loosely coupled or non-coupled processes. The timing property values inside the .lib lookup table generally don't depend on each other. The different processes may talk to each other or with the main dispatcher to indicate the job is almost complete and the CPU is ready for another SPICE job to be assigned. But aside from that, there really isn't a string of dependencies to consider. After the results information is collected and written to the output.lib, the process is complete. So this brings up a couple of key points for us. First of all, this is a loosely coupled pool of many tasks, with each individual task taking a relatively short time to complete compared to the overall sequence. So the job dispatcher should be intelligent enough to order and dispatch the SPICE simulation jobs to maximize the utilization of the CPUs. Secondly, a lot of data is being written to the .lib files from the different processes or the main dispatcher process. So disk I/O operations per second or IOPS and metadata access may become bottlenecks. The library characterization software must be optimized to reduce these operations, and we also want to consider the disk bandwidth requirements in our cloud configuration. With those considerations in mind, the diagram here shows an example of a configuration for our cloud characterization deployment. This, of course, isn't the only way we could set up our cloud infrastructure. For example, some configurations use a hybrid model where jobs are sent either to the cloud or on-premises servers depending on workload. But I think this example provides a good basis to conveying the baseline components required for cloud characterization. The main considerations here are security, performance, and cost effectiveness. For IP security, we control access to the servers and disks via secure access points. The landing server in this case is the gateway to access our cloud resources, and we have protocols put in place to prevent unauthorized access. Data transfer to the cloud should also be done using encrypted methods. The main source of cloud computing performance and cost will be from the SPICE job execution nodes. For large-scale characterization jobs, having thousands to tens of thousands of CPUs seems to be the optimal amount, because within that range, we're able to complete most large-scale characterization jobs within 24 hours. That amounts to thousands of virtual machines, depending on the number of cores per machine chosen, of course. So it's important to work with your EDA partner and cloud partner to choose the correct machine type. We talked about disk bandwidth requirements for library characterization earlier. Here we have to make sure we're using adequately high-performance storage solutions, such as a high-speed network-attached disk or a parallel file system. Otherwise, overall scalability will be gated by disk access regardless of how fast the CPUs run. In addition, a cluster management system is needed for provisioning and deallocating execution nodes dynamically. We want to be able to spin up virtual machines as needed to run SPICE and then shut them down when they've completed their batch of jobs. The last thing we need or want is execution nodes being active and costing us money while not being used to run jobs. Along with license management and load balancing, these tools are essential for completing our cloud characterization flow. Depending on needs, we could combine them to run on a single virtual machine to save cost, or split them into their own virtual machine for flexibility. So in the previous section, we explained what it takes to build a secure, high-performance, and cost-effective cloud deployment. Here we'd like to summarize at a higher level some of the best practices that help us obtain the benefits of deploying to the cloud. One thing we realized pretty quickly was that we were working a whole lot closer with other teams internally, such as our IT, DevOps, and InfoSec teams. This helped us get started quickly to a secure and effective working environment on the cloud. External partners are also essential in this transition. Aside from cloud platform partners, since any Foundry and third-party IP used will be uploaded to the cloud, it's important to work with Foundry and IP partners to make sure the IP is transported, stored, and used correctly. Major foundries have cloud ecosystem programs in place to facilitate this. Another point is to know the cloud configuration options available. Cloud platforms have been in use for a long time in many other industries, So a lot of applications, managed services, and tools are available that can make our jobs easier. This, of course, is a double-edged sword because sometimes we can get overwhelmed with the choices available. So it's important to communicate with cloud and EDA partners to know these options and which ones are suitable and applicable to our workflows. Tracking KPIs to optimize workflows is a good way to make sure that we're getting the most out of our cloud deployment. After all, one of the advantages of using cloud resources is the flexibility to change our hardware and software setup easily. If a different VM instance type is working better, we can make the switch to a different VM relatively easily compared to, say, investing in a new on-premises server. Other components such as disk bandwidth allocation can also be tweaked. There are many KPI tracking mechanisms available from both EDA software and cloud platform tools, all that which can be used to identify performance bottlenecks and how to fix them. And last but not least, please reach out to us if you or your team are considering cloud deployment. At Mentor, we work actively with our cloud partners like Amazon Web Services and Microsoft Azure to test and validate our workflows so that our customers can minimize the trial and error needed and quickly achieve the benefits of working on the cloud with our tools. Next, I'd like to show a case study of running Mentor's library characterization on Microsoft Azure Cloud. In this case study, we had worked with Microsoft to validate our library characterization tools and analog fastspies on the Microsoft Azure Cloud Platform. Since most on-premises compute clusters for library characterization consist of up to a few thousand CPUs, we wanted to test the scalability of the overall solution when pushed to using up to 10,000 CPUs on the Azure cloud. In addition, we also wanted to identify and validate a cloud configuration for library characterization using Azure's virtual machines, cloud storage, and other high-performance computing tools. So for this collaborative effort, we use Azure's HC44RS machines, which are part of Azure's H-series virtual machines for high-performance computing. For runtime storage, we use Azure NetApp Files, which is Azure's first-party cloud storage system. We also use Cycle Cloud to dynamically spin up and deallocate virtual machine instances from our tools Job Dispatcher. The HC44RS virtual machines have, as you may have guessed, 44 cores each. So for the 10,000 CPU runs, we were using 228 virtual machines. Results-wise, we demonstrated close to linear scalability, comparing our 10,000 CPU runs against runs with a lower number of CPUs, as we show in the graph to the right. Now, this didn't really come as a big surprise to us because of the reasons I'd explained earlier, but the validation of the results and the real-world implications are actually quite significant. A common scenario for on-premises library characterization is running on 1,000 CPUs and taking a few days of runtime to complete a characterization job. That same job becomes just an overnight run using 10,000 CPUs on the Azure cloud. We've just talked about one of the main benefits of running on Azure, which is potentially reducing runtimes from a few days to a few hours. This means engineering teams can kick off a characterization run in the evening and come back in the next morning to see the results instead of having to wait a few days. In addition to that, engineering teams that are competing for on-premises hardware resources can access compute resources in the cloud during peak workload times. Some of our customers are already doing this. They're complementing on-premises compute clusters with cloud servers so that hardware availability doesn't become a bottleneck in product schedules. I'm going to talk about the fourth point here before coming back to IP security. In a lot of on-premises server systems, new batches of machines get added as IT invests in expanding compute capacity. So what we end up with is batches of machines with different specs. Also, sometimes the local server queue would add someone else's job to the same machine that's running our job, depending on how the queue is set up. These are really not showstoppers per se, but in order to increase the predictability of job runtimes, it's nice to have or be able to have machines of all the same spec and dedicated to our task for the duration of the task. All this is possible when running jobs on cloud resources. Coming back to the point about security. Now, this is an important topic since we're talking about transferring data off our networks onto the cloud. From a business perspective, cloud providers like Azure in this case are equally vested in securing their network from outside threats, just like we are with our data. So I think the key points to consider are how data is being transferred between cloud servers and our on-premises machines, how the access points for the users are handled and secured, and how we're ensuring data and access allocated for us within the cloud network stays completely within our own access only. For these points, our IT and InfoSec teams work very closely with Microsoft to identify the security protocols needed, and we've been using them throughout our projects on Azure. Finally, I also wanted to mention that the close collaboration between our development team and Azure means that for our mutual customers, if there are questions or issues that come up, these are addressed together with frequent communication between teams so that our customers don't have to go back and forth between us and Azure. Earlier, we had released an announcement on the validated readiness and scalability of our tools on Microsoft Azure, resulting from our collaboration efforts. So if you're interested, you can take a look at the press release or just reach out to us and contact us for more information. Okay, on to our summary. We went through a lot of information in this session, including all the considerations and options to ensure security, performance, and cost effectiveness of deploying library characterization workloads on the cloud. What I'd like to emphasize here is that the resulting benefits of investing in the robust and secure cloud characterization flow are quite notable. In addition to being able to burst through high priority characterization jobs overnight, instead of waiting for days of runtime, cloud platforms also provide a resource pool to address peak compute capacity demands so that production schedules are not delayed by hardware limitations. Mentor's AMS verification tools are cloud ready and tested, such as Mentor Spice simulators, AFS and Eldo, as well as Solido Variation Designer and a library characterization platform. We work closely with cloud providers like Amazon Web Services and Microsoft Azure to provide validated workflows and optimized tools for our customers. This brings us to an end to this presentation. Thanks again for joining us, and I would be happy to answer any questions you have.